morning, everyone. I am Aayan, Year 8 SEY2 or AW from Prince of Wales Island International School. I am making this video for my States of Matter homework.
Ooh, I learned about states of matter in school.
Nice. There are solids, liquids, and
gases.
Exactly.
I don't know, but I feel something's wrong with my stomach. I feel bloated.
This is my brother, the gas man. The Ray man. He is from 5RA at St. Christopher's International Primary School, Penang. Now, let me tell you what topics we will be covering in this video. The particle theory, diffusion, the Brownian motion, and finally, gas pressure. So let's get started.
Started? I'm already done. What a relief.
Do you really need these glasses?
Yeah, I love them.
Nah. Do you really need those glasses?
Yes.
Nah. Perfect.
Would you mind bringing them back, please?
Fine. Follow me now. First of all, we will be looking at the particle theory.
Ooh! What's the particle theory? Do I know about it?
I was just about to. Never mind. The particle theory was proposed by the philosopher Democritus. He theorized that the world was made up of tiny building blocks called atoms and particles.
So, what is that related to solids, liquids, and gases? And why is it important?
Aha! Glad you asked. Solids, liquids, and gases are all made up of particles. And every particle moves and vibrates ever so slightly. But the motion is so small, it is impossible for the human eye to detect. The difference between solids, liquids, and gases is how those particles are arranged.
Arranged? Like I arrange flowers in a vase, or books in a bookshelf, or notes in a song, or files in my computer, or my enemies' faces, or in an array, or...
Slow down, Rayyan! None of those are what I mean. Except maybe for rearranging your enemies' faces. Although, I wouldn't advise that because then your lawyers would be arranging bail for you. Anywho, let's rearrange this conversation, shall we? In solids, the particles are arranged tightly in regular rows, all touching each other. Something like particles in an array. This explains why solids cannot be further compressed or poured. And yes, it also explains why solids cannot flow.
Oh, that's right. I cannot compress this rock further. That means it is a solid. But wait! How do you explain this?
I got it! It's because there are air holes in the sponge. So, when you compress it, you are letting the air out. And this means that the sponge is actually a mixture of a gas and a solid. Oh, and it's because the particles in this solid has a high elasticity rate.
So, solids cannot be compressed. Wait, does that mean liquids can be compressed? So can I take water and compress it? Can I?
Oh, water is not a solid, yet it cannot be compressed. This is because the particles of a liquid do not allow it to be compressed either.
So both solids and liquids can be compressed. But then how would you squeeze juice, which is a liquid, out of apple, which is a solid?
Elementary, my dear Rayyan. Matter is able to change state under certain conditions. So, you can change a solid fruit into a liquid juice. Oh, and some of those fruits may leave behind a solid pulp. I will take you down memory lane and talk about how material changes. Just for you, Rayyan.
So, what are the particles like in liquids? And what are the particles like in gases? And
Whoa, calm down and let me tell you. Also, is it possible for you to ask one question at a time? Or is that just not in your programming? Anyways, questions aside, let me give you some answers. The particles in liquids are arranged loosely, just touching each other. This explains why they cannot be compressed, but can flow and be poured.
oh yeah! See, I can pour sand from one hand to another. So does that mean sand is a liquid?
No, the grains of sand in this clump of sand are arranged in the way that the particles of liquids are arranged. Each grain of sand is its own lone solid. Anyways, let's pass some gas. Let's move on to gases. The particles in a gas are arranged very, very, very loosely, more so than a liquid, and fly around randomly. They can be compressed and flow and be poured.
You said that a solid, like apples, can change into a liquid, like apple juice. So, can we also see a liquid turn into a solid? And can we change between all three of them?
I'll be showing you some of them, but the complete list is melting, freezing, condensing, evaporating, deposition, and subliming. But we won't be doing those experiments right now. Drum roll, please. We will now be doing time travel. Yes, you heard it right. Now look into my eyes. Give up your mind. Go back in time. 3 years ago, when I was in year 5.
We're going to see how melting affects material changes. First, we need some ice. Ice is a solid material. We're going to leave it to melt in this glass. As you all know, the melting process will take a long time. So, we're going to see another material change. Can you tell me another way of changing a material? Boiling. Since Rayyan's blood is already boiling, how about we boil something useful? Like an egg. Look, it's all gooey like gel. But by the time we're boiling it, it'll be a near solid. Now to light the stove. Boiling will take a while, so I check on the ice. It's done, but you can't let this perfectly good water go to waste. Refreshing. Melting is a reversible change. Or you could have taken the water and put it in the freezer and it would have frozen and become ice again. See, and freezing is also another way of changing materials. Now for the egg. Rayyan! Coming! The blue cloves eggs. He will be gobsmacked when he finds out that the raw egg was a material that changed into a boiled egg when it was boiled. Use the spoon to put it in the bowl. I'm going to peel the egg. Rayyan cooked the egg. See how the egg changed from gooey to near solid? Rayyan, dig in! Yummy. And Rayyan, if I hadn't took the raw egg and boiled it, it would not have turned into this wonderful boiled egg. So changing materials is not all to pot. In fact, it is exciting. When it comes to changing materials, I know my onions.
Oh hush, now is not the time. I'm eating some scummy eggs. Anyway, don't be so shush. Disappear now. Bye.
What happened?
Aha! Now you must be wondering why we skipped so much time and appeared over here.
No, I'm wondering why we stopped looking at what was happening.
Didn't you see? The memory was burning and there was glitching. If we had stayed any longer, it would have been destroyed forever.
No!
Exactly. Now we'll understand how materials change state. So, solids melt because when the heat affects the particles in the solid, it gives them energy. And that energy causes the particles to expand and change state. And when we freeze juice to make popsicles, the low temperature saps the energy from the particles, making them move slower and slower until they reach the point of a solid.
Oh, I get it. But wait, doesn't the knowledge just evaporate away from your brain?
The particles of my gray matter must be strong to not let the particles evaporate so easily. Speaking of evaporation, do you know that when the liquid particles get heat, they break off and fly and become gas particles? Like when water heats up and boils to become water vapor.
Oh, so the ice melted in the experiment because the heat in the air went to the ice and broke its rigid formation, turning it into a liquid.
Exactly. And do you know that when water evaporates and spreads into the air, making the weather humid, it is displaying a phenomenon called diffusion.
Oh, so diffusion is when you take one thing and put into another thing. Like if you put food coloring dye into water and the dye spreads in the water?
Close. Diffusion is when particles of a higher concentration move to a lower concentration through a permeable or semi-permeable membrane. But for it to be fully diffused, the dye or material has to be spread equally throughout the whole substance. We will now try and test diffusion.
Oh boy, oh boy, oh boy. Can we dye in the water?
What?
Can we kill the water?
You seem to be having a lot of violent thoughts. Let me try and see if I can diffuse the situation. What are you trying to say?
I meant to say to color the water. Can we dye the water? But that didn't sound grammatically right. So I said, can we kill the water? But that doesn't sound right either now, does it?
Oh, I see what you mean. You mean you want to put the colored dye in the water and watch it diffuse and change the color of the water.
Exactly what I said.
Well then, your wish is my command, master. Your wish is my command, master. Here's the dye and water.
Awesome! Can I put the dye in?
Maybe later. First we gotta go to the kitchen. Sure. Now you can put the dye in. Now the coloring will diffuse. Remember, it has to be spread equally throughout the mixture. Come, we'll go to another room.
What's next?
I think we should talk about the
Brownian movement.
I think you mean the Brownian motion.
Exactly what I said.
Yeah. Before we look at what the Brownian motion is, let's look at its history.
there was a Scottish guy named Robert Brown, right? And then...
Wow, that's correct. Rayyan, what's that you're hiding behind your back? So that's how you knew about the Brownian movement.
Okay, I'm caught.
Never mind. So yes, a Scottish biologist by the name of Robert Brown did observe what is now known as the Brownian motion in 1827. He observed pollen grains jiggling and vibrating under a microscope in his pool of water. But he couldn't explain how it happened.
The pollen is probably swimming. After all, it is kind of a living thing.
That's what Brown thought. But when he tested the same experiment with dust did the same thing. And dust is definitely not a living thing. So nobody could explain why this happened until the 1870s when the particle theory was proposed. The particle theory explained that the particles in the liquid caused a tiny involuntary force which caused the pollen grain to move.
Hence, the Brownian motion.
Yes, the Brownian motion.
Exactly what I said.
Anyways, now we'll talk about gas pressure.
What's gas pressure? Is it the bloating I feel when I need to pass gas?
In my opinion, the name is pretty self-explanatory. It's when you compress a gas and the gas has less space to move around, so it more frequently collides with the other gas particles and with the walls. This creates a lot of pressure, and that pressure is called gas pressure.
But is gas pressure the only way to speed up the particles? Doesn't heat speed them up?
Yes, that's actually correct. In fact, a container needs gas pressure inside the container so that it can retain its shape. Otherwise, it will implode.
This is because outside the object there is gas pressure. The pressure is pushing and bumping into the container.
Yes, to neutralize and nullify the external gas particles, there needs to be some gas pressure inside the container.
A balloon is a clear example. When you blow into the balloon, the CO2 particles go into it, which helps it inflate.
Without the gas pressure created by the CO2 inside the balloon would not be able to retain its shape and would deflate.
But with too much pressure, the object would explode. Is that why we pass gas? So we don't explode? Can we explode something?
No, Rayyan, we will not explode something.
Oh. But we have a vacuum. We can do an implosion.
No, Rayyan, we have a vacuum cleaner, not a vacuum. But we can look at some videos of a small-scale implosion and a large-scale implosion.
Yay!
Oh,
That was epic!
No, it wasn't. Wait until you see the large-scale implosion.
You're right! That is epic!
Now that we've done gas pressure, let's go back to the diffusing of food coloring. Let's head back to the kitchen. Yes, now that's fully diffused. You see how the dye has spread completely throughout the liquid?
Yes.
Well, that's diffusion for ya. Wow, it's already nighttime. Well, we did have to look at the things that make up our very existence. Because, like, particles make up everything. Oh, never mind. This is Kidspective signing off. Bye.